For joining us for our semi-regular series on climate impacts and climate adaptation. I am Susan Dickerson Lang. I'm the director of the UW Climate Impacts Group, and I am going to kick things off today, and then we'll hand things off to my co-presenter and collaborator, Dr. Emily Howe, in just a few minutes. So again, thank you for being here today. We are really delighted to be joined by so many folks. For 30 years plus now, the UW Climate Impacts Group has worked in partnership to build climate resilience by advancing awareness of climate risks and supporting science-based action to manage those risks. We are a group of about 20 research scientists and communication and education professionals at the University of Washington, and we also have a huge number of collaborators and partners across the region. Our work encompasses lots of different components of climate science, climate extremes, and climate adaptation across our region. The Climate Impacts Group is inclusive of our programs that support Washington State as a resource for knowledge and action. We also host the Washington State Climate Office, as well as some large federal centers located here in the Pacific Northwest. The Northwest Climate Adaptation Science Center, which is a USGS program, is hosted here, as well as the Northwest Regional Integrated Science and Assessment Program. So today's presentation, we are going to dive into one component of the work that we do here at the Climate Impacts Group, which is action-oriented research to support climate adaptation and building climate resilience. Like I mentioned, I'm going to start things off and provide some background and a little bit of context related to the previous research. And then I will hand things off to my collaborator, Emily Howe, to talk about our most recent study on snow storage effects from forest thinning. So as I mentioned, I am the director of the Climate Impacts Group, and I'm also trained as a hydrologist. And my background and passion is really in watersheds and watershed processes. And so I've spent a lot of my career looking at climate and climate change influences on future snow and stream flow. And this plot that we're all looking at right now is a graph of historical stream flow in the dark blue line with the top peak, and then some projections of future stream flow, all in the Yakima River as measured at Cle Elum River, at Cle Elum, Washington, taking away the effects of regulated storage in the upstream reservoirs. And so as we look into the future of stream flow in the Yakima River, as well as most rivers across Washington and the Pacific Northwest, we see this really distinct signal of climate warming affecting snow storage, which is then affecting the amount of water available in stream for fish and aquatic habitat, as well as for out-of-stream uses. And each one of these colored lines is just stepping through time, going from the near future in the light blue to the end of century in pink. And some of my first exposure to working with the Climate Impacts Group was actually in doing work like this. And so the Climate Impacts Group worked a lot on this about 15, 20 years ago, doing some of the first studies in this region. And now these data are publicly available and useful for planning around our region. But this, as a master's student at Western, when I was first working on this, got my attention because, you know, as we're thinking about future stream flow, we're looking at future water shortages. And I became really interested in what are the potential ways for us to buffer some of these effects. And that led me to think a lot about the influence of forests on snow and stream flow as well. That simultaneously as climate is changing and affecting snow and stream flow, our forests are also changing. There's forest harvest. We see forest thinning in this aerial image on the left. You can see thinned forest on the left, and then patches that have been cut for wildlife habitat in the center part of the image. And of course, wildfire is a huge driver of forest change in our region. And so that has really led me to the question of how does forest change and climate change combine? To what extent could we either utilize forest management or leverage forest change to dampen some of the climate change effects on stream flow and snow? And to what extent could they even potentially amplify those? Um, and in particular, I've spent a lot of time looking at forest influences on snow processes. We know that forests, and therefore forest change, influence individual snow processes. The forests intercept snow and rain, which, as it's then intercepted and stored in the canopy, it's either melts and drips, it melts and evaporates, or it sublimates, resulting in less snow under the forest. The forest provides shading from sun and sheltering from wind, slowing snowmelt processes. And the forest also re-radiates energy in the form of thermal radiation, which leads to faster snowmelt, at least locally, resulting in things like tree wells or small patches of melt around trees. And these different processes that are modified scale up to a net effect on snow storage. And so we can look at a gap on the left and a forest on the right that are adjacent to each other. So they're subject to the same elevation and the same climate. And we can look at the same day, in this case, an April day in 2019 in the Cedar River watershed, and note that although there's more than a foot of snow still in the gap, the adjacent forest is almost bare. And so we're affecting both the amount of snow that's stored and the duration of storage on that landscape. But depending on how all those individual processes combine, the directionality of the net effect can actually flip. And so we can look at a different location. In this case, we're at Snoqualmie Pass. And same story, but an opposite effect, where most of the snow is gone from the gap, except on the very shaded edge, while there's still over a foot of snow in most of the adjacent forest. And so this directionality obviously is really important to the storage of snow in terms of the timing of that storage and then the timing of that release and contribution to stream flow. And so the change in net effect led some of my previous research. As a PhD student at UW, I spent a lot of time in the Pacific Northwest taking snow observations across the gradient of climate in our region. We've got a huge climate gradient west to east. We're looking at a map on the upper left here of winter temperature, ranging from our warm and wet maritime conditions on the West Cascades in red, getting cooler as we cross over to the East Cascades into this sort of transitional climate until we get all the way to the east into Idaho and Montana, and we're approaching a much colder, drier continental climate. And so we collected data all across the region to try to understand what are the climate drivers and the different drivers for whether the net effect of forest and forest change is to retain snow or to accelerate the disappearance of snow. And what we saw was a lot of variation in forest open pairs and some distinct cases that we tried to define. So we looked a lot at pairs of forested areas and open areas that are right next to each other to control for aspect and elevation and climate. And on the right-hand side is a conceptual picture of all of the different flavors of forest open pairs that we've seen. The black line is looking at snow through a given winter in the open area. So that just an open area like that gap on the bottom left, which is located at a snow-tell station. And each one of the colored lines illustrates a way in which the adjacent forest and the snow in that adjacent forest could relate to the snow in that open area, ranging from the dark blue line, where there's a lot less snow in the forest and it disappears a lot earlier, to the pink line, where there's a little bit more in the snow in the forest, even than in the open, and it lasts longer, and several cases in between. So the observations of these different cases and the drivers really led us to develop a spatial hypothesis of where do we expect to see these different cases play out across the Pacific Northwest and the Western US. And we tried to map them based on winter temperature and spring temperature and precipitation and topography to make some spatially explicit hypotheses as to how forest management or forest change from disturbance like wildfire might affect the timing, the amount and duration of snow that's stored on the landscape. Um, and each one of these numbers on the map, if you kind of look, there's some little white numbers. Those are areas where we actually have data. So keep in mind that this map really is a spatial hypothesis. We took what we learned at a handful of sites and extrapolated based on what we think those climate drivers are. But I want to point out that there was a major data gap in the Eastern Cascades. Not only do we not have actual field sites at that point in the Eastern Cascades, but that climate, that transition between maritime warm and wet and continental dry and cold is really underrepresented in snow studies across the Western US. And that brings in my collaborator, Emily Howe, who we started talking about this about a decade ago. And she pointed out that the data gap in our forest snow understanding coincided almost perfectly with some of the high priority watersheds in the 20-year forest health strategy. The Department of Natural Resources prioritized, along with the Forest Service, different areas for forest health treatments like thinning and prescribed burning to reduce future fire risk and also to improve forest health. But we didn't quite know. We have a guess and a hypothesis as to what would happen here, but we didn't have data. And so Emily and I started working together to take on this very applied question with direct applications to the work of our state's agencies. And we developed a transect of sites shown in the map on the left, trying to span the gradient from the West Cascades to the East Cascades. We deployed poles and cameras and temperature sensors and all sorts of remote equipment at each one of these sites to try to measure snow and snow storage across these different climate areas. And briefly, what we found is that on the west side of the Cascades, which is the graph we're looking at now, which is Mount Gardner, circled in the map on the left, we saw what we had seen previously in some of the work that I had done, which was really focused on the West Cascades, which is if you follow the blue line, there's a lot more snow in the forest gap represented by that blue line, and it lasts a lot longer. It takes farther in the season for it to get to zero than the snow represented by the green line, which is the adjacent forest. And that the thinned forest, represented by that orange line, with a canopy cover somewhere in between the forest and that gap, was somewhere in between. This was not a surprise. We'd seen this in the Western Cascades before. And then as we moved into the Eastern Cascades, we saw that the differences were much diminished, which fit quite well with our spatial hypothesis, that as we get into that colder climate, we see less of an interception effect and less a muted effect overall of gaps versus forested areas. And so essentially the effect of forest thinning or forest change in some of these zones is largely neutral. We don't see a large amplification or dampening of that signal. But we did have one site that piqued our interest that was our lowest elevation site on the Eastern Cascades. And on that site, we actually had a north-south contrast, whereas in the other sites, they'd been largely flat. And we saw quite a difference between the north-facing site, where there was a lot more snow in the gap represented by that blue line than in the forest in the thinned area, whereas the differences were much smaller on the south-facing side. So this piqued our interest and led us to the Clay Elm Ridge study. And as we sort of moved into the study that Emily's going to tell you about, I think one of the takeaways from our Eastern Cascade study is that gave us a much better sense of hydrologic resilience. And in fact, that's Emily there on the right thinking about hydrologic resilience as we are out in the field with our partners from DFW and from the Department of Natural Resources and the Forest Service. And as we're talking about different forest health treatments around the region, everybody's bringing their own perspective around wildlife habitat or carbon, or what are we doing for fire risk or forest health. And what Emily and I started talking about in the course of these conversations was the real need to take what we learned about forest thinning effects on snow storage from the standpoint of forest versus open, and really start to drill into what is the gradient of effect across real applicable forest treatments, which led us to this next study. And so in just a moment, I'm going to hand it over to Emily and introduce her. But I just want to point out before that moment to say that the joy and the value of a collaborator who is such that you have a person that can really push you to think differently. And that has been the wonderful thing about working for Emily for me for the last decade or so, is that she and I have both deeply been in this work. And whereas I think about things from a very detailed process perspective in the snow hydrology world, she's really helped to push me to think at the landscape scale as to how do all of these puzzle pieces fit together as we're thinking about climate change and management, and snow and water all as one holistic package. And so that has just been really lovely. And Emily's a fantastic snow buggy driver, which also has been helpful to our collaboration. So with that, I'm going to introduce Dr. Emily Howe. She is the senior aquatic ecologist at the Nature Conservancy of Washington. She's also affiliate faculty here at UW in the School of Marine and Environmental Affairs. And not only does she have expertise in snow and upper watersheds and water hydrologic resilience, her work extends all the way down to the estuary with some fantastic work on the Stillaguamish Delta and climate change and fish habitat. So she's got one of the most holistic pictures of climate resilience from sea to top of the mountains that I know of. And so with that, I'm delighted to hand it over to Dr. Emily Howe.
Thank you, Susan, for that very kind introduction. And thank you all for being here today. We are going to switch who gets to share now and dive into some of the work that Susan and I have been doing, the tail end of the last 10 years or so. But yes, as she mentioned, I am first and foremost a fish squeezer. And so I only have expertise in the upper watersheds and snow because of her. But I work for the Nature Conservancy, and part of my job is to really support their land stewardship practices. And so in 2014 or so, TNC helped conserve over 48,000 acres in the Central Cascades of Washington and became one of the major land stewards as a result. And so we really had to think about, how might we actually support these lands best through hands-on management practices. And so I want to draw your attention to this photograph here in front of you, which is of the Teanaway Valley with the enchantments or the Stewart Range behind them. So this is what it looks like on the eastern slopes of the Cascades for those of you who might be tuning in from further afield. And while the mountains in Mount Stewart and Annapurna are very beautiful in the background and all spiky, it's the foreground I want you to look at, which is that green carpet of trees. And Susan sort of brought up the issue of wildfire and landscape change. But I want you to note that this photo is a really good demonstration of what happens to a fire-adapted Western dry forest after a century of fire suppression. It is a very dense forest, and I want you to recognize that that is not its historical forest structure. It would have had frequent fire moving through the system, whether that would be cultural burning or lightning strikes, but it would not have had this dense carpet. So keep that in mind as we move forward, because that landscape change, hang on, got to get the buttons to move. That landscape change can exacerbate some of the climate impacts. And that's one of the things that we're really trying to figure out how to intersect here at the headwaters of the Yakima Basin in this case. So we're going to kind of walk through some of these sort of dual climate crises that are bearing down on this eastern slope of the Cascades. And that is this intersection of wildfire and drought. So some of you may know half the story real well, and maybe not the other half, and some of you may know the other flip. But let's walk through sort of what's happening in the state in terms of wildfire. So the current risk is rising and the costs that are associated that with rising. But I want you to notice that the highest area of risk is right along the eastern slopes of the Cascades. That's all that dark red area, and it kind of arcs up into north central Washington. And This is a photograph of a pre-post sort of photograph with about a century in between of what these landscapes looked like before wildfire suppression was sort of the main one of our main management activities, right? And so on the left-hand photo there, you can see that there are sort of individual trees, there are sort of clumps of trees, there's broad swaths of open meadows, and there's some area where it's denser. And so that's sort of the natural historical forest structure for these types of ecosystems. And then as you move to the right-hand photo, you can see it's been replaced by a really dense carpet of really fairly even-aged trees. And so if we think about how fire operates in a fire suppressed forest versus an ecologically managed forest, you can step through these sort of two columns of pathways forward. In the fire suppressed forest, you'll notice that, right, not only is it denser, but there's it's multi-canopied forest. And so that creates what we call ladder fuels. And so when fire comes into the landscape, it has the ability to rise up from the forest floor and climb into the canopies and then spread between the crowns. So we call that a crown fire. It can be very high severity and it can be stand replacing. So you might have heard of catastrophic wildfire. That's sort of another term that is applied to these sorts of situations. It's not that that type of fire never existed before. It absolutely did. It's needed, but in a more patchy type of situation. And it was also paired with much more beneficial wildfire that was low. So if we think about this moniker of good fire, it's you want to slow it, you want to spread it, and you want to sink it. And so a landscape that looks more open, has this reduction of ladder fuels, that is where you can have a slow spreading sunk kind of a fire that has really beneficial and really needed effects on these fire adaptive ecosystems. So they evolved with it and they need that fire. And so then you get this sort of patchy mosaic. And so over the course of time, fire has shifted from a stabilizing feedback mechanism and driver in these dry forest ecosystems to a destabilizing feedback mechanism. And that's because we have a fire deficit problem. So it may be sort of odd to hear me say that we both have, too much fire, wildfire risk is rising, but we also don't have enough fire. And it's all in the type of fire that we're experiencing and the frequency of those fires. So one path forward and able to get more fire on the landscape to kind of move ourselves back into sort of ecological sort of balance with fire is that we need to start doing mechanical thinning work throughout these high wildfire risk areas. And so in that map, you can see that's DNR, where the high risk is, and then the black outline plots are where those are the sort of the management units, the forest health planning units. And so as soon as Zen mentioned earlier, that sort of overlaps with this climate transition zone, where we don't really know what the relationship between forest structure and snowpack response is. But that's where all of these thinning units are going in place. And it looks like selective logging, but it is more towards an eye to creating these openings and these gaps. So it's called ICO thinning. So it's not evenly spread stands. And so here on Clay Elm Ridge are some before and after photos of some of the thinning work that our forest management team implemented with a team of local loggers. You can see there's a huge ponderosa pine in the middle. So you leave the really old fire resilient trees, you clear out a lot of the underbrush, you masticate that stuff up and chop it up into little bits. And then you leave these sort of larger spaces in between the crowns of the trees. And once you've done that, the land is now kind of prepared to receive fire again. That might be in the form of a prescribed burn. It might be in the form of a cultural burn, or perhaps a lightning strike, or a campfire, a chain that sparks from a car going by, what have you. But the land is more prepared to receive fire in a beneficial way. So that's our primer on fire ecology for now. Talk to the fire ecologists if you want more depth, because they got it. But the next thing is, how does this then intersect with drought? So Susan, mentioned that forest structure has a profound impact on snowpack response, but that impact can be really different and can have absolutely opposite effects depending on where you are. For us this year, as you've been paying attention to, I'm sure you are, it's not been a good snowpack year. It's been a pretty dismal one. Here in the Yakima Basin, we're sitting around 32% of normal as of April, which is kind of when we sort of thinking about how we're going to allocate water across the region. And if you look at the lower plot, we're this sort of like black line in terms of how much snow water equivalent we have as a state compared to normal, which is this green line. And so that's pretty abysmal. But believe it or not, we're actually doing better than a lot of the American West is this year, where a lot of the Southwest has about 0% of its normal snowpack. And so while 32% of normal may be pretty darn painful, it's also important to just recognize that we have a lot more water than many areas nearby. And it means that every drop counts. So yes, when Susan and I met each other, we were, found ourselves up here on Clay Elum Ridge. Me as a fish squeezer, trying to think about how to support TNC as they looked at this new land and tried to figure out how they were going to manage it. Most of that forest management work was focused on wildfire resilience and forest health treatments at the time. But Susan being Susan and me being me, and this being the headwaters of the Yakima, we couldn't stop thinking about what those treatments might have for water. And this is because the Yakima is identified as one of the most climate vulnerable basins in the state, in part because it is dependent upon snowpack for 75% of its water supply. When the area gets water, it comes in the form of snow. And then it is metered out over this the melt season, but it doesn't really come in the form of rain for the most part. And so when we have a bad snowpack year, that has ramifications for the social and ecological resilience of the whole valley. This is an area that has robust and threatened and endangered salmon runs, other anadromous fishes that are supported or protected by tribal treaty rights. It is an area that supports a $2 billion agricultural industry. And we are now in a state of declared drought, particularly acute for the Yakima, which has already implemented water rights restrictions or curtailments. So not only is the Yakima one of the most climate vulnerable basins in the state, a lot of that's actually because its headwater is actually not that tall or high elevation. So you just kind of run out of air or land up there to hold snow. And so the lower elevations, you get more snow melt cycles, you get more snow on rain, and you get more, snow that should have been snow actually falling as rain. And the Yakima is not alone as one, but it is one of a handful of very vulnerable snow-dependent basins throughout the American West, where it is, among a handful that are dependent upon snow for over 75% of their needs. And so it's a really critical place to investigate this question, and having a lack of data wasn't helping us really know what to do in terms of these wildfire resilience prescriptions. And so we really started thinking, okay, well, how can we start to restore water to this landscape? Where should we do it? And so that's what led us to the sort of overarching management question, which are these wildfire resilience prescriptions that are opening up the forest, right? Are they compatible with our needs for hydrologic resilience? And we started with these really simple metrics of snowpack depth and snowpack duration, because these are the water towers of the West snow. The Yakima reservoirs can only supply about 30% of the needs. And so it's that big, broad landscape of snow holding that makes the difference. But it's tricky, right? So here we're sitting on Clay Elum Ridge. We're looking across the Clay Elum Lake Reservoir at sort of the near ridge there. And you can see there is a big clear cut with no snow on it, except for right along the edge. There's some dense forest areas that you can't really tell what's happening under there. And then there's a thinned area that seems to still have snow in the ground. And that elevation seems to be kind of different than what's happening in the upper elevation slopes as well. And this is where conversations with the Tuppish Forest Collaborative that we work with became really useful. Susan showed that picture of us kind of out there pondering things with all of our partners. So the forest collaboratives are set up in different parts of the state. originally to kind of manage fire very well because fire sweeps across ownership boundaries so that the whole landscape could be managed as one. And so the Tuppish is the one that we work with at the Nature Conservancy in the Clay Elum sort of upper Yakima area. And that's the U.S. Forest Service, Department of Natural Resources, Department of Fish and Wildlife, Yakima Nation, and ourselves. And so together we kind of narrowed into this question of, how might we maximize snow storage, and how might we actually measure that? And so as a private NGO landowner, we have a lot of flexibility at TNC to implement kind of creative land stewardship activities. And so we were able to work with our forest management team to implement experimental plots within their wildfire prescriptions, but for snow work. And so that's one of the places where TNC's sort of as an entity becomes a real research asset for the community at large, because we have some more flexibility compared to some of the agency landowners, for example. Okay, so here we are. Susan kind of walked through our first study, just being like, what the heck is happening with just gaps and openings? And now we're at this stage of saying, okay, let's figure out how we can maximize forest snow storage through these fire resilient forest treatments. And I would be remiss if I didn't highlight Cassie Lambrazo, who was a PhD student and postdoc with us, and she was really focused on this as her work and really led a lot of the nitty-gritty modeling for this whole team. So our project goals were really first to quantify snowpack storage across this gradient of different thinning levels. The forest management teams were very clear with us that openings and closed canopy was not terribly helpful to them. They also needed us to crosswalk forest management metrics that they use, such as basal area, with the snow hydrology metrics. Sky view fraction, for example, or is more important when you're thinking about canopy interception. And then to provide some management recommendations. And I throw this photo up here because it's a picture of me, Cassie, and then Herman and his dog Remus. Herman is a TNC forester, and so he's the one who helped create the forest management plan and work with the local logging teams to actually implement the experimental design, which looks like this. So the ridge runs east-west, so we have a north-facing slope and we have a south-facing slope. We had a bunch of different individual plots within different thinning units. And then we have down at the bottom, you can see there's a gradient of colors. Those are these basal area sort of metrics that are used by foresters. So if you would imagine cutting all the trees down in a forest unit and then measuring the surface area of all the trunks per acre, that's what basal area is. So really high basal area is a lot of trunks, very dense. Low basal area is just what it sounds like, very open canopy. And so we measured snow response with snow on LiDAR. The first time was fixed wing, the second time was with UW's rapid team with LiDAR based. And these were both the first one was the first snow on LiDAR data set for the state. As Susan mentioned, we also threw out a bunch of cameras. These are sort of point measurements, but they go through time. And then we measured snow density, all pre-treatment and then post-treatment. So first thing we did, or Cassie did, was to really calculate a change in forest structure before and after treatment so that we could actually know, did we do something? Herman will say, of course we cut down the trees, and then we need to say, but by how much, right? And so the top panels here are showing changes in canopy height, pre-treatment, post-treatment, and then the change between them, the difference in canopy height. And the second panel is looking at distance to canopy edge changes. So that's kind of a measure of gap size. You can think of it that way. And then the bar plots at the bottom are looking at how basal area actually relates to percent canopy cover. And you can see that's actually not a very strong connection. So that crosswalk between basal area and things that matter for snow is kind of weak. And that created some messes for us later on. The next thing we had to think about was to measure snow between the 2 years, knowing that snowfall is going to be different from one year to the next. And so we calculated a standardized depth value in order to compare among the 2 years, or between the 2 years rather. All right, popping through some of the results. Here we're looking at time series results from the cameras. So the cameras are put up on these trees, they're focused on these snow poles, and then we basically just look at the photos and mark down what is the height of the snow day by day as you go through the season. So the colors here are related to, in the top panel, those basal areas, with greens being denser forest and moving into reds being less dense forest. Or gaps. And the bottom two panels are looking actually at the same thing, but with sky view fraction. And what we can see is that on the couple patterns emerge. First of all, it's a lot messier when you're trying to look at patterns with basal area compared to sky view fraction. So as far as that crosswalk is concerned, basal area is a tough one for us to be able to go directly from there and tell you what snow response should be. Sky view fraction works. And if you look at those two photos at the bottom, you can get a sense of like what interception might look like in a closed versus more open canopy, right? So that's kind of intuitive in this area. The second thing we can see is that in those lower two panels, you get this nice progression from the greens all the way up to the dark reds, meaning that as sky view fraction increases, we consistently get deeper snow, but only on the north side of the ridge. On the south side of the ridge, the darkest red lines, those most open sky view fraction plots, fall in the middle, which means that there's not a lot of tree or shading protection happening there. So we can start to see that there's different dynamics happening on the north versus the south side of the ridge. And as Susan mentioned earlier, we are seeing a duration effect, particularly on the north side, of up to a month on the north side of the ridge. So that all made sense. So the next thing we tried to do was to say, okay, that's what happens at a point location. What happens in terms of total snow depth in a forest thinning unit when you are trying to describe it by basal area? The first thing I'll say, so these are cumulative distribution curves. And a really simple way to think about these is that if you are sort of in the upper left-hand corner, higher and further left, that's going to be lower snow depth, so shallower snow. And if you're kind of moving to the right and lower, that's going to be deeper snow. So that's sort of how these relate directly to kind of what you think about on the land. And what we can see in the upper two panels in terms of snow depth is that there's a lot of spaghetti mix. So if we try to like pull this out by basal area and relate it to snow depth, there's it's hard to kind of can squint and kind of get a pattern and be like, yeah, it's kind of greener, shallower, but red kind of the other side. Same thing when we look at sky view fraction, gets a little bit clearer, but for the most part, when we try to connect snow dynamics to basal area, it's pretty messy. So we said, okay, let's go with LiDAR-derived forest metrics as opposed to these assigned ones. So the first thing we needed to do was say pixel by pixel, did it change? And if it changed, was it a result of a treatment or is it a result of forest growth? Right? So there are some ways that a pixel could change just because trees continue to grow over a couple of years. And so they might have closed in. And then there are other areas where we actually took the canopy out, right? And so a tree could have gotten closer to a canopy edge, or it could have been taken out completely and become a gap. So the first thing we did is try to decide for every pixel, what was treated, what was not treated. And then to calculate those cumulative distribution functions again, and to kind of say, okay, if we just look at distance to canopy edge, how does that spread happen? And what we can see is a much stronger effect on the north side of the ridge. Those lines kind of spread out from one another with the opening, those blue lines indicating that's where we did a more aggressive thinning, increasing in snow depth in a positive way. And the green lines not doing that increase. So we can see that stronger treatment effect on the north facing slope. And that is matching up with what we saw in our time-lapse cameras. But we still had this question of like, okay, but then what's the optimal gap size? And how do we get at that, given that the basal area factors are not being very clear for us? So here we use distance to canopy edge, and we kind of broke it into these categories of dense forest, sparse forest, edge areas, small gaps, and large gaps. And we plotted it again before and after treatment on the south side of the ridge and the north side of the ridge, and things started to kind of unravel and become clearer, right? So we can see these bigger spreads happening on the north slopes. We can see it transitioning from red to green. Again, those large gaps operate interestingly, which means there is an optimal gap size, which is about 4 to 8 meters in diameter, maybe a max of 16 meters. Or another way to think about that is around 1 to 2 tree heights. And when we, so that's sort of an important recommendation, right? These small gaps. We're not talking about huge ones. We're not talking about even thinning, even spacing thinning. We're talking about the same types of treatments that are going in for fire resilience that match the natural forest structure, which is that individual clumps and openings, the ICO prescriptions. And the result in terms of overall increase in snowpack depth at the sort of whole treatment scale of the ridge, south-facing slopes increase snow through the thinning by 16%, which is equivalent to 5.1 acre-feet of water per 100 acres. And on the north-facing slopes, we had an increase of 30% snow storage, which is equivalent to 12.3 acre-feet per 100 acres. So in conclusion, we were very pleased and very relieved to find that our fire resilient strategies are compatible with the hydrologic resilience needs of the area, and that we had local data to actually inform that. It was perfectly reasonable to suggest that they might be crosswise with one another and that we would have to do some prioritization, but it's really lovely and relieving that they overlap in a positive way. And so these forest treatments to reduce wildfire risk are increasing snow storage at this site. The treatments on the north-facing slopes are especially good at enhancing snow storage, so we might think about putting more gaps in on those north-facing slopes. Canopy cover is really the metric that makes the difference as opposed to basal area. And it's these small to mid-sized canopy gaps that are useful. The bigger ones we tend to see melting out or not gaining as much snow over time. So those are our main sort of recommendations. And I think it's important to fold this into how we might step our way towards the future from where we are now. So what this means is that mechanical thinning is really setting the stage for water and fire benefits. And there was a recent paper by Furness et al. that says, wildfire and forest treatments can mitigate, but cannot forestall climate-driven changes in stream flow regimes. So our data and their data are both showing that these forest treatments can have a pretty good effect, and that they can't forestall climate, but they can restore some of the lost water that this landscape has experienced. They also say that we need to really think about how we might reduce the fire deficit and what is the mechanisms by which we do that. And so one of the things I like that they said is the key to achieving benefits is that fuel reduction and climate adaptation treatments be strategically applied to facilitate more wildfire and not less. And that is one thing that these wildfire treatments are doing, right? They're prepping the land to be able to receive fire in a beneficial way. And then finally, they say, reducing the existing wildfire deficit is a key part of climate and wildfire adaptation strategies, and intentionally preparing landscapes for fire using landscape restoration principles, such as ICO, can result in more desirable wildfire effects. And I think with our data, we would also submit, it can also result in more desirable hydrologic effects. And so with that, I will thank you all for coming, and we would be more than happy to take any questions. And I just want to thank the whole team of people that have been involved in this project over the last 10 years or so. It's been a true joy to work with everyone, particularly all of those of you who are so good at your quantitative modeling skills. So thanks much.
Fantastic. Emily, thank you so much. I have worked with you for lots of years, and I learned some things listening to you through that talk. So I really appreciate you walking through that for us. So I would invite folks to put questions in the chat or via the Q&A function. I will monitor both, but maybe I will go ahead and kick things off. and just ask from the perspective, Emily, of your work with the Nature Conservancy and lots of partners, including the Tapash Forest Collaborative, like how actionable are the recommendations that came out of this study? We made real efforts to try to make sure we were thinking about the forestry side and the fire fuels treatment side, but how close are we to actually being able to draw not just a dotted line, but a solid line? And then I see some questions coming through, so I'll move to other folks after that.
Well, I would love a forester to tell me how they could include sky view fraction in their forest, in the planning of their forest units. I don't think that's a place that I'm particularly well qualified to discuss, but I think that we're getting closer there. Um, I also think that, one of the things that we found is that pretty much any of the sort of thinning, we're going to get a water benefit for pretty much any of those thinning levels. And so I think back to some of the conversations we've had on the land, with all the partners, with I'm remembering a particular forester, and she's like, we have to manage for a lot of things. There's wildfire, there's wildlife, there's timber, there's water, you kind of go down the list, there's insects and disease. And she's like, when it comes down to it and it's me on the land, I can kind of think about three at a time. And so for me, one of the most important things here is that we found that we are synergistic with what the wildfire prescriptions already are. And so when it comes to hydrologic benefit, we don't really need to do anything different than what those prescriptions are already sort of offering. We might think about, hey, north facing slopes is a place where we might put in a few more gaps than we do now, because we often think about the south facing slopes in fire resilience prescriptions because they're hotter, they're drier, they're tinder compared to those north facing ones. But for me, it was like, because they were synergistic with one another, that's the best possible answer. We don't have to choose one or the over the other. So that makes it pretty darn actionable.
Fantastic. Thanks. Okay, jump into a few questions. The first question is related to characterizing the effects of these treatments across different forest types in the Cascades. For example, west side moist and dense forests versus higher and lower elevation. I'll just briefly answer this for us and just note that part of this study was really focused on the Eastern Cascades because it was such a data gap. And that data gap really aligned with the hotspot for forest treatment, which is why we were really motivated to get some answers to help understand the synergy that, or not, we were worried that it may be an or not that Emily was just talking about. But I would say, we have a pretty good handle on the west side of the Cascades and that maritime climate, that opening gaps in particular leads to more snow lasting longer on the landscape. And as we move into the more continental, drier climate, we do get to a situation where we can open up gaps and openings that are too large, so that we actually generally retain more snow within the forest. And that Eastern Cascades area is really kind of the sweet spot in between, where we're seeing that either a neutral effect on snow storage at some of our colder, higher elevation sites that we studied in the first study that Emily mentioned, and then this north-south effect that we're seeing at Cle Elum Ridge, which is slightly lower elevation. Then moving to the climate context, Emily, Jimmy from Department of Ecology asks a great question here about how does this affect scale in different years hydrologically? As we're dealing with a really below normal snowpack this year, for example, how would we expect these results to change, or do they just simply scale up or down?
Yeah, I think it's a really good question. And Susan presented those photos of opposite effects that Snoqualmie Pass from her PhD research. And then we went back and we had a site there again in what had been a poor snow year, right? And originally when Susan had done that, it was a different effect. So we had opposite effects at Snoqualmie Pass depending on whether it was a good snow year or a bad snow year. And so I think there's a lot of questions still in place there. And man, I wish we had cameras out there this year. It would have been.
Oh, I know.
But me, it's so hard to protect. So yeah. I think that I just wonder if some of the teams out of California would have some good intel on that. They fly LiDAR, snow on LiDAR twice a month.
in
down there
places.
um, to get at that question, or um, because I do think there are going to be transition areas that are going to do funky things. I don't know, Susan, can you elaborate
Yeah.
on the why you think behind why Snoqualmie passed flip-flopped?
I, well, Snoqualmie Pass, it seems to be right in that climate zone, and we know that climate is really driving what that net effect is. And so where Snoqualmie Pass flip-flops based on whether it's having a warm or cool year or high or low snow year, it can act more like a west side forest or it can act more like an east side forest, just really based on that both winter and summer or winter temperatures, spring temperatures, and the timing of snowmelt all play into those climate drivers. Emily, moving on, you mentioned fire quite a lot in terms of the context, but there's a great question here from Thomas Timberlake about the effect of fire itself on the results that we saw. We did all measurements in these mechanically thin situations, whereas prescribed fire may have a different effect. Could you speak to the fire effects on snow storage and what we might expect to see differently or the same if we had done this with prescribed fire instead of mechanical thinning?
Yeah, I mean, I think that instead is a tricky one, right? But I think we couldn't have done prescribed without the mechanical thinning first, right? So it's a mechanical thinning and then prescribed. Um, we are now in the process, TNC is doing prescribed burns on the ridge. So we're in a position where we would be able to run that follow-on experiment. But what we do know from some really good work was at Portland State with Kelly Gleason, and she's looked at the effect of black carbon on snow and calculated sort of the diminishing albedo effect, right, and the increase of sort of solar radiation heating up that snowpack and melting it out early. So that is actually the exact next question that I think we have is to say, okay, if this is what we're trying to do, is to do these mechanical thinnings, prepare them for prescribed burns, and then running them through that process, what does that mean for a snow response? But that has to also be taken in the context of what if it wasn't a prescribed burn that came through? Jolly Mountain Fire came through this area in 2017 and got very, very close to this particular area on the ridge. And that is there were some areas that are fully stand replacing. So there's going to be a gradient of wildfire prescribed burn intensity that I think warrants some investigation for sure. And it may be that there's this sweet spot in terms of how you do your prescribed burns and the frequency of that too, because the frequency is going to likely shift the temperature. I would imagine. I'm getting outside of my lane here as a fish squeezer, but the more forest fuels you have, the longer you leave the land, the more forest fuels you're going to have, and then you're going to have to think about what does that mean from a fire perspective in terms of
Yes.
temperatures and black carbon that would then be floating back down onto the snow, which can persist for up to a decade.
Yeah, great. And maybe switching gears from this, forest effects to removing trees, there's a great question from Ann Savory about, are there any implications for how we replant? Like, are there applications here for replanting after clear cuts or fire in terms of snow retention?
I mean, I think from if we can just get away from evenly distributed systems, we're probably doing good things. I mean, that holds on the west slopes of the Cascades and the Olympics, where an old growth forest has a lot of patch dynamics in it. Same thing on the east slopes of the Cascades. So even age and evenly distributed trees are generally problematic. So I would think about actual densities, right? I don't know enough about how seedlings what sort of dynamics they need to be successful recruits. Do they need each other? Could they be separate, spaced out? Those are questions I don't know how to answer. But I would say if we could shoot for sort of a patchy mosaic, that would be the ideal.
Excellent. There's two questions here that get at the how do you scale up in terms of if we were to apply these everywhere. So one is a question of what are the effects if we scale up, which I will say is a question we would love to answer and have ideas to do so. We just haven't found time or funding to get there yet, but that's on the horizon. And then Bob Mitchell notes that there is a gap component of a hydrologic model called DHSVM, where we worked with PNNL to build that into the functionality of the model so we could represent snow dynamics. And that would be a great next step too. I've chatted a bit with Ning Sun at PNNL through time about trying to both use these observations to test the model in this region, as well as using it for a tool to scaling up to that larger landscape scale that matters a lot. And so then maybe to thinking about the larger landscape scale, I want to conclude just with one more question, and that's Emily. I know you work a lot in the Stillaguamish Delta on endangered Chinook and Chinook habitat. Thanks for letting me come out with you once to help count fish. It was a great learning experience for me, but given your broad scale, what are the sort of the dotted lines that you can make between the work that you're doing in the Stillaguamish Delta and the work that we're doing, hundreds of 100+ miles away and thousands of more feet elevation in the Clay Elum Ridge and Clay Elum watershed?
Oh, my favorite question, because I'm really an estuarine person, so I feel very comfortable there. Um, yeah, I think the Upper Yakima does not drain down into the Stillaguamish whatsoever, but there are really strong impacts of river flow and stream flow on estuarine species. And in 2015 was one of the first big snow droughts that we experienced here. And down in the Stillaguamish estuary, the plants didn't even set seed that year. They were so salinity stressed. They senesced early. We weren't measuring fish at that point in time, but it was a really clear signal that when we have bad snowpack years, we have stressed marshes. Similar to sort of this landscape change of sort of really strong anthropogenic reforming from fire suppression in sort of these western dry forests, the floodplains and estuaries have had a really, a very similar dramatic change to them, which is in the form of levees and dike systems that have really separated those areas from sort of the pulse of the tide and the pulse of the floods. And those rivers have been sort of straitjacketed in between the levees. And so with the water that does come down, comes down as a fire hose and it shoots off into sort of the deeper waters of the bay, rather than kind of holding that freshwater lens in the delta, where all of these transitional species need that freshwater lens. And so in the Stillaguamish Delta, we've now just completed, in collaboration with the Stillaguamish tribe, one of the first distributary channel reconnections throughout the Salish Sea. So we've created more off ramps for the river to spread out. And so far we're seeing species like Chinook and bull trout that are hanging on later in the season than they ever have before, in what is one of the worst snowpack years we've had on record, which is, the fish will come back, but they don't hang around in that estuary very long because they just can't. But it's pretty phenomenal to see that when we do roll back these legacy imprints, we give them a lot more space to handle climate impacts like a bad snow year. So
Fantastic.
thanks.
Excellent. I love that. When we roll back these legacy impacts, we give some more space for climate adaptation. That's a fantastic thought to end on. So I want to end there. If folks have questions we didn't get to or want to chat more, please reach out. Emily and I love talking about this work and are delighted that you all joined us today. Thank you for being here, and thanks, Emily, for the great presentation. Take care, everybody.
Bye, everyone.